Welcome. Good afternoon, everybody. And welcome to our Science Thursdays with Brookhaven Lab. The goal of Science Thursdays is to engage our student and education community in STEM topics by meeting Brookhaven Lab STEM professionals and learn more about their work, their career path that got them to where they are today. At the end of this 45 minutes, we hope that that what you heard today will spark your interest in a STEM career and perhaps consider being part of the Brookhaven Lab community. I am Aleida Perez, and I'm from the Office of Educational Programs, and I'm glad to have you here today. And I'm joined by my colleague, Salvador Gonzalez, who will be managing the Q&A portion of today's discussion. Before I introduce today's guest, we have a few reminders. Couple of things. You are welcome to submit your questions in the Q&A chat section. We will try to get as many questions that we can. And if you have any difficulties with the stream, the video, or anything regarding the Zoom, you can let George Canales, our IT support here today, by making a comment on the chat section. Okay. So today I am joined by Carlos Soto. He is a scientist in the Computational Science Initiative here at Brookhaven Lab. And Carlos will share with us today the work that he does at the laboratory related to machine learning. But we also will talk a bit about also his career path and to learn more about, to how the path that he took to get to where he is now. Carlos, welcome.
Hello, great to be here.
Thank you. It's a pleasure to have you here today. And looking forward to today's discussion. Just to get the ice broken a little bit, when you and I were talking a bit, you mentioned that you were a sci-fi nerd, a sci-fi buff. So what is your favorite movie? What does that mean?
Well, I love sci-fi in books and film and everything. Far too many to count, but most recently I have really enjoyed Dune. So if you guys haven't seen it yet, it's back in theaters. Go watch it. Oh
yeah, it's pretty good. It's an awesome movie. Great. I know that you have been at BNL not too long. How many years have you been at BNL so far?
4 years now.
And where were you before BNL?
Before that, I was at Texas A&M University finishing my PhD.
Oh, cool. So I know you have a slide to share with us because what you did as a graduate student at Texas A&M is, built into what you're doing today at Brookhaven Lab. So can you tell us a little bit about what were you doing at Texas A&M as your graduate work?
Sure thing. Let me share my screen real quick. So hopefully you guys can see that.
Cool.
So at Texas A&M, I was part of a robotics research laboratory. And our research concerned robots for use in search and rescue. We used robots in real search and rescue scenarios using air, sea, and land robot assets. And my research concerned interactions both with the personnel who were using the robots as well as with the victims who would be interacted with on the victim side of a robot interaction. So it meant a lot of generating of user interfaces as well as a lot of perception algorithms. So for example, if a person cannot speak, maybe gesture recognition is a useful mode of interaction. But in order to make that happen, you need some algorithms that can recognize hands and so on. And so a lot of my research tied into, even though my research was robotics, it tied into machine learning, computer vision, artificial intelligence. And there was also some toy problems, like you see here on the screen. There was like some video game playing AIs, like playing Pac-Man automatically with multiple goats that can collaborate with one another against Pac-Man. It was pretty fun work.
That sounds like a very, very fun thing. So some of the robots that you work on, were just in testing mode, or you actually were taken into very live, real events or actions?
So my advisor in graduate school, her name is Robin Murphy. She pioneered the field of search and rescue robotics, and she actually deployed to real disasters, including Hurricane Katrina, 9/11, the Fukushima nuclear reactor incidents. I personally did not deploy with these teams, but she deployed with first responders and with the robots.
Oh, that is an awesome, very, very, very cool. So the research that you did at Texas A&M and with machine learning, it's what had brought you here to Brookhaven Lab at the Computational Science Initiative. So for those of us that may not be aware what the Computational Science Initiative is, to be very frank, you are my first guest from that department. Can you let us know what is the goal of the mission of the Computational Science Initiative, and perhaps what kind of projects or research goes on at the group?
Yes, of course. So the Computational Science Initiative, as you said, is a little bit newer than the other directorates at BNL. It does two types of research. It does foundational research in computer science, everything from machine learning to networking to high performance computing and quantum computing. But we also do applied research where we take new methods that have been developed in the computer science community and look for applications of relevance in the domain sciences across BNL and with our partner institutions as well to find good fits between application and method.
That's very, very, very nice. And I have to digress a little bit because I just missed this question that came on the chat, but it's related to your work at Texas A&M. It's just an idea how much a unit like the ones that you were working at Texas A&M will cost.
The robots, you mean?
Yeah.
Robots are quite expensive. The robots that we were working with tended to be on the order of $100,000 to $200,000. So very, very expensive. More recently, some robots have become much cheaper because they've been commoditized. So like UAVs, you can buy a UAV for $1,000 now. And it can do a lot of the same things that you could do with the earlier generation, very expensive robots.
Thank you, Carlos. Thank you. So thank you for sharing the mission, what the CSI department does. So what is your role at the Computational Science Initiative?
My role is as a researcher in machine learning. So I do research in machine learning and especially in natural language processing, which is a subset of machine learning.
Right. So for the folks here that might not know, what is machine learning? When people hear, what does that mean? I mean, machine learning. So you're teaching the machine to do something, right? So can you expand? Can you let us know what does that mean?
Yes. So machine learning is it can become quite a buzzword nowadays, along with artificial intelligence. Just for clarification, machine learning is one type of artificial intelligence. And it's very difficult to define artificial intelligence, a much broader field, because that goalpost is always moving. Once you solve a problem, it's no longer AI, now it's something else. But machine learning is about solving problems with data. So rather than trying to hand tune exactly how a program is written, and a person sitting down and writing all of the rules for what a program needs to do, machine learning is about taking data as the source to learn the rules that the program needs to follow in order to accomplish something, in order to infer something or learn or do something. So machine learning is a data-driven discipline in computer science.
So that data that's informed, I guess in that the data informs then the decisions that those algorithms will make in terms of the resources that you bring.
That's right.
And so, like you said, it's a buzzword, right? Everybody talks about it. So, how is it? I know we're going to talk a bit about your particular area of interest, but in the general sense, how is machine learning or perhaps AI used or applied in day-to-day activities, for example?
Well, machine learning is starting to enter a lot of parts of everyday life. So if you have a smartphone, you're intimately familiar with machine learning already.
That's true.
So the fact that you can talk to your phone and it can respond, that is machine learning at work. Every commercial product at a very large scale that you interact with is very likely is using machine learning. And in the sciences, we're applying machine learning to try to solve some of the problems that have been difficult to traditionally address because of the scale of the problem, because of the size of the data, or because of the nuance of the patterns that need to be recognized, which are very difficult sometimes for humans to interpret. And
now that you mentioned, and we will get now to what you do, but I wanted to say that now that you mentioned about day-to-day phones and day-to-day, even when we do those searches in those search engines, right? And they learn our patterns into our likes or dislikes, more like our likes, right?
Yes,
and they do, and every time you search for something and just keep popping those ads or those pieces, and so that is machine
That's an important application of machine learning. It's commonly called recommendation systems. So YouTube learns the kind of things you like to watch. It'll recommend you new videos. So does TikTok, so does Google, so does Facebook, everything does.
Yeah. So that's actually very good for our folks to be aware of, or to understand that that's how it happens. So you mentioned that your area of research has to do with natural language processes. And I know you have a few slides that you're going to share with us to explain to us what does that mean, and how it's used, in machine learning. So you want to share your slides?
Yes. So let me get back to these slides real quick. So natural language processing is about applying machine learning techniques to text, to writing and speech in the way that humans produce writing and speech. The way you and I are communicating with one another is not the normal way that machines interpret data, but teaching a machine to interpret natural language is something that has been, that a lot of improvement has been made on in recent years. And we can apply those improvements called natural language processing to scientific data as well. Because one of the problems with scientific data is that a lot of the results in science are published in the literature, which is very, very large. We're talking about millions of documents. And if you are a scientist working on a particular problem, you don't the disparity between published genomes in plant biology and the amount of information that we actually know about what these genes do. Now, a lot of that information is actually present in the scientific literature. You see here on the right-hand side, these green highlighted regions. Those are names of genes and proteins, and the scientific literature has descriptions of what these genes and proteins do, how they're interacting with one another, but there is no easy way to get all of that information out conveniently for a person to search through in a natural way, like the way you could with Google search or something like that. But we can use machine learning to recognize these entities. You see that the way these are all written looks very differently. Sometimes it's a number, sometimes it's parentheses, sometimes it's a natural language word. But recognizing that these are all the same class of object, that these are all proteins or gene names, is something that we can train machine learning algorithms to do.
So if you train your machine to find proteins, for example, then you can then do a big data search to search for articles related to that particular, I don't want to say cohort, but at least that particular class of what you're looking at.
Yes, and you can go beyond that too, because once you have a lot of these automatically annotated documents, you can do some meta-analysis that you would never be able to do manually. You can look for patterns across thousands of documents and look for every instance of this particular gene and every other gene that it interacts with, and try to look for patterns that would be very difficult to find otherwise.
What do you do with the information that, with all those searches that are, how the data is found, how it is collected or preserved?
Well, that is a part of a partnership that we are involved with the domain scientists. In this case, it's with biologists. And so they tell us the kinds of problems that they're trying to address, and we try to work on the tools to help them address those problems.
Very, very cool. Very cool. So you mentioned this example. Do you have, so besides, I'm guessing that this language, natural language process, you can use it for any kind, not just scientific literature, right? You can use it for any kind. Are there any other examples, besides searching for literature, have you worked on any other type of example or the projects that uses the natural language processes?
Well, most of my research in natural language processing has been in the scientific literature, because it is a big problem in and of itself. Just to give you another example of some of the challenges that occur here, possibly a lot of people in your audience have come across the situation where you have a PDF document and you're trying to copy and paste text out of that PDF document, and you paste it into Word or something, and it's all garbled. It's a garbled mess. That's because the way that PDFs are encoded is great for making the document look right, but it's not great for making a machine able to read it automatically. And that's a problem regardless of what application you're trying to apply this to. And since a lot of the documents that we deal with are in PDF format, this is one of the big challenges. And so we're working on methods to automatically extract these contents in a much more clean way using machine learning. And we can go beyond that as well, because there's always new opportunities for new techniques that weren't possible before. Since we can recognize which parts of a document are which different classes of information, we can now take information out of not only the text, but also the tables or the figures, process that for, apply that for further processing.
That's actually very cool, because as an experienced person, you know, I have done that, and you're right, it's garbled. When you do it one, you can manage one, but you cannot manage, you know, thousands of them. It becomes quite impossible. That's like a very nice application.
Yes, and once again, you hit an important point, that this is a problem of scale. You can do this for one document by yourself. You can do this for one table by yourself, you know, edit it in Excel or something. But if you want to do this for 10,000, you're not going to do that by yourself.
No, unless you have, you know, 10,000 graduate students to do that, which is impossible.
I would prefer to apply machine learning. I was a graduate student not so long ago.
I know. So that's just very cool. You know, one thing that that you and I also talk about the machine learning piece is this whole that you can take you know, similar processes that you're doing with machine learning and perhaps a natural language process to kind of reverse engineer this scientific data. And when you told me that, I thought it was probably it opened my eyes in ways that I have not even thought that you could do that. So can you share a little, can you tell us, what do you mean by that reverse engineering scientific data that you can do with machine learning?
Yes, of course. So as many people know, the reason we publish in science is so that other people can use our results, our methods, our data for further advancing the science. And so the scientific record is an integral part of the scientific process. But the problem with that is that if you have contents in your scientific record that are very difficult to access, then it really impedes the progress of science. And here we have a problem where a lot of times, in fact, very commonly, the results in your papers, the results in your documents are produced in graphics like this, in charts and in plots. And they're great for a person to visually interpret the data, but most often there is not a table accompanying this graphic that contains those results. So I can look at this graphic and see, okay, that red bar is about 12, the blue one is about 11, the yellow one is about a little bit less than 4. And once again, it's a problem of scale. I can do this for one graph. I cannot do this for a very large number of graphs. And so we can again apply machine learning to this problem of scalability. If this is a task that a person is able to do visually, then there is an opportunity for a machine to be trained, for a machine learning algorithm to be trained to try to extract the same kind of information. And again, we can reverse engineer the contents of these graphics, of these charts, to produce them in a format that can be processed automatically, like a table, for example. And this is quite new research, and I think it's quite interesting because the same method that we developed for this problem can be applied to very many different types of graphics. On the right hand side, you see here, you can use it for pie charts, you can use it for line graphs. Anything that you can interpret as a series of dots, this same method can be applied to.
And I'm guessing that once you extract that data, that information, it can be, one computationally use it to kind of data reanalysis or a better understanding of the data that was generated. So there's it's a different way of looking at the data that we all share and publish, and how we evaluate that information that is out there. This is, like I said, this is probably the most cool thing I ever heard. I think it's just fascinating.
And I agree. That's one of the most, at least for me, that's one of the most exciting parts of this work. The fact that you can reanalyze data and analyze data at larger scales than was previously possible. So machine learning isn't just about doing the work that a person can do. It's about enabling scientists to do new things that they couldn't do before.
For this reverse engineering, do you have a specific groups that, do you have a specific fields of science that are most interested in exploring this kind of tool to look back at all results? I'm probably have a little, I remember back in my day, perhaps I'm thinking papers that were published, that were all papers published long time, a while back, that there might not have the either is it readily available, or the information was preserved in a different way. I'm guessing that tools like this are most helpful. So is there a specific group that has field of science that are looking into this with more care?
Right now, the field that I'm working with is again biology. It's plant biology for functional genomics for plant biology. We're working with a collaborator at the Joint Genome Institute, which is also part of the DOE. But I expect that if this pans out and works as well as I hope it does, which so far it looks like it is, I expect to see interest from other groups as well.
Like I said, it was very cool. So what other group projects? I know that with using your research interest and expertise, what kind of projects are you working on right now?
Well, as I said, most of my research is natural language processing and document related, but not all of it is. Another project that I'm on is about applying machine learning to inform nuclear reactor non-proliferation and inspection tasks. So the next generation of nuclear reactors, which are being researched today, are going to operate in some ways quite differently from today's reactors. One of the candidates for this type of reactor is called a pebble bed reactor, where your fuel is contained in a ball about the size of a baseball, and these fuel pebbles will cycle through a reactor. But in order to ensure that the fuel in these reactors is being used safely and according to regulations, you need to keep very close track of how used up the fuel in these pebbles is. And the way you do this is by taking some spectral measurements. You take a measurement, you use a sensor to take a measurement of the fuel. But that is what these graphics here show. The center chart in red and the right-hand chart in black show what this data looks like once you take a measurement of this signal of the gamma spectral reading of the fuel pebbles. But then from that signal, you have to predict how much of the fuel has been used up. And the traditional way to do that is by looking at specific peaks in these graphics. And you see kind of the little spikes in these charts. You would select specific spikes and you would measure how tall that spike is compared to a different spike. And you take the ratio between them, and that correlates with how much of the fuel has been used up. That's a linear regression problem. But it turns out that if you're doing that by looking at one specific spike or a small number, let's say 2 or 3 of these particular spikes, you're throwing away most of the data. Whereas machine learning really outperforms prior methods when it is fed as much data as possible. So you can feed a machine learning method this entire signal and use it to predict the quantity of fuel that has been burned up already much more accurately than you could with traditional methods. And that's what we're doing to try to improve the quality of these measurements that are being designed and developed for nuclear reactors of the future.
So that's actually very cool. So the scalability issue, not necessarily that there are not just the data number, but the wealth of the data that you have.
That's
in
right.
terms of the points that you're getting from that single reading from that sensor. So
that's right.
So that's just as addressing that problem as well. This is actually very cool. So you can then have a more accurate number, for lack of a better word.
That's right. You can improve the accuracy of this task, and you can also improve the time performance of this task. Because for this particular problem, the fuel pebble needs to cool down, like actually temperature cool down a certain amount of time before you can take the measurement. But the longer it cools down, the more storage space you need in order to do this process. But if you use a machine learning method, you can let it cool down for a shorter period of time and thereby reduce the amount of infrastructure, the amount of material space that you need in order to do the same task. So you have a double win there. You have improved the accuracy, and you've also reduced your operational cost to do this task.
Very, very nice. Very nice. Is this widely used right now? Is it quite commonly used procedure in this? Or are we just are we still in the testing process of
This
this
is still in
method?
the testing process, and
Mhm.
it's quite new to apply this kind of method to this particular problem.
Very, very cool. Anything that you can think, so, like I said, machine learning is a buzzword in AI and all, so where do you think we're headed next in general for the
Well,
field?
one of the challenges of machine learning,
Mhm.
as I've said a few times, is the data. You need a lot of data in order to build successful machine learning algorithms. But not only do you need the data, you need labels for that data. You need to
Mhm.
teach the algorithm what it is that you want it to learn from the data. You needed to teach it what the correct answer is. But a lot of times getting that correct answer, getting that label is very difficult or very expensive, or sometimes it's completely infeasible. So the direction that machine learning has been moving recently, and probably will for some time, is in improving the quality of machine learning methods that do not need these labels, that do not need
Got
the
it.
right answer, that can still learn something useful even from unstructured, unlabeled data.
That's very cool. So if I understand you correctly, the when you mean unlabeled, the quality of the data doesn't really have. You're referring, is that refers to the quality of the data itself, or is that something completely different?
It refers to the quality, but much more, it refers to the metadata that accompanies the original data. So the stereotypical problem that people think of when they think of machine learning is looking at images and recognizing pictures of cats and dogs, for example. If you have 1,000 pictures of cats, 1,000 pictures of dogs, 1,000 pictures of horses, and so on, and you tell a machine learning algorithm, these are pictures of dogs, these are pictures of horses, and so on, it will learn what a picture of a horse looks like. But if you have a million pictures of animals and you don't tell the machine learning algorithm which animal is which, you no longer have the labels. That's what I'm talking about.
Got it.
But an algorithm should still be able to learn something useful from that data, and that's the direction that machine learning is heading to now.
Yeah. So they're still animals. Sorry, what animals are they? But you still, the machine learn that they are animals and not plants.
Right. Or it could learn this is one type of animal. I don't know what it's called. These are all the same type, and this is all a different type.
Very cool. Very cool. You're welcome to put any questions in the chat if you like. And so we will address those questions as they come in. Carlos, I think one thing that we're going to pivot a little bit to your career path and a little bit about, you share that you're a sci-fi nerd, and that's how, and that, but there's more to, we know that there's more to you than that. So my question, when you and I were talking, we talk about your career path, and we do have a number of high school students and college students in the audience. Can you share with us, what was that path? What was the motivator that say, hey, I am going to be a computer scientist? I mean, as opposed to other career choices that we might have.
Well, as a child, I always loved the sciences. I was quite good at math. I loved learning, especially, and I loved tinkering with things. I was the child who took everything apart and tried to put it together, sometimes even successfully. And so for in my case, it was a very clear path towards the STEM fields in general. So I knew that I wanted to do something technical. Once I got to about high school, that's when I started playing around a lot with computers myself. I come from a poor background, so I didn't have a lot of the opportunities that some other people might have had. I didn't have a computer until I saved up for a very long time and finally bought a computer in high school. And I tinkered with everything there was to tinker with that computer, and I found it fascinating. I didn't know what programming was, but I knew that I wanted to make the kind of things that make a computer go.
Yeah.
And so when I got to college, I decided that computer science, computer engineering was probably something that interested me. And I just dove in, feet first, right into the deep end of computer science as a discipline. Even though I didn't know all that much about it, I knew that it interested me just conceptually. Once I was in college, I had an opportunity to do an internship at HP, Hewlett Packard. And I got a lot of hands-on experience with actual, production level computer science. Later, near the end of my undergraduate time, I had an opportunity to do some undergraduate research And that introduced me to the whole field of science, which is quite different from engineering. And that fascinated me like even so much more. So I immediately knew, okay, I need to do research and I need to go into graduate school. And I never looked back from there.
That's awesome. Yeah, sometimes so it's just having that curiosity, I'll say, the interest of just of the topic. And for some of us, that just simply is just what motivates us to go forward. There's a
Yes.
question on the chat that said, what advice would you give high school students who would love to follow your career path or would like to be a researcher?
Well, first of all, learn the basics of the discipline that you are interested in. In my case, computer science. You should learn as much as you can about coding. I did not have an opportunity to take coding classes in high school. I didn't
Okay.
understand anything about it until I was in college. But if that had been an opportunity available to me, I would have immediately wanted to jump on that. And I strongly encourage any students in the audience to take every opportunity they can to learn about programming and not just the fundamentals of how to do basic things, but also try to get a little bit of hands-on experience with it. Try to build something with you if you can. There's so many resources today across the internet for self-learning, and it's enormously important that you engage in self-learning, not just in part of your school's curriculum, but learn on your own time as well. And build something that you're interested in. Build a little video game. Build something that you think is fun. And it's in the process of building something that you learn a lot of the things that you would never have known otherwise, because failure is the best teacher, and you're going to fail a lot along the way into building something that you think is useful. So that's my advice there.
That's a great advice. Not just I love when you said not just don't learn the basic, right? How to code, but how do you apply that coding into perhaps putting something together? And I think that's just very valuable, very very wise advice. So what brought you to Brookhaven? That's my question to you.
Well, around the time that I was job hunting near the end of graduate school, I had basically 3 career paths open to me. I had academia, so go be a professor. I had industry, go work for Google or Facebook, or go to the national labs. And I hadn't known about the national labs until relatively late in my graduate career. And I'm very glad that I learned about the national labs, because for me, it's the perfect fit. It is the right balance between the freedom of academia and the resources of industry. Because a lot of the very interesting science that is out there to do requires significant resources, more than a lot of universities have access to. A lot of large computation, a lot of large data, a lot of domain science expertise that you won't find in any one particular institution, you can find across the national labs. But at the same time, you don't have the constriction of domain of problem that you're looking at that you do in industry. So Google has all the money in the world, but they're going to look at the problems that are going to make Google money. The same thing is true for Facebook, for Amazon, for Apple, etc. And I'm sure they're great companies to work for, but I wanted to have the freedom to explore research that interested me. And the national labs struck that exact right balance for me between freedom of research and then resource access.
Yeah, and that's very good. And so that's actually awesome. And you mentioned about the resources, and I think the national labs, I think, bring that collegiality, like you mentioned, the academia piece, that you can, talk to the folks in biology or talk to the folks in chemistry and see, how that collaborative effort in terms of the science that we do. One thing that you also mentioned was internships, and I know you mentioned so how important were those internships in your path?
Enormously important. It's a cliche, but there is so much that you don't learn in school, and until you get some hands-on experience doing this for a company, for an entity that has some stake in the game, then until then you don't actually know a lot of the details that really make your field work. In computer science, I had learned a lot of the basics, a lot of the fundamentals of computer science. I had taken the basic classes, data structures, algorithms, a lot of that stuff. But once I got into working for HP, I realized that yes, the tools and the techniques that I learned in class were useful, but not necessarily in the way that I thought they were useful. And I also had to learn a lot of stuff on my own for my job as an intern that I would not have learned in class, just because it was part of the requirements of that job. And it really encourages that self-learning that I was talking about, because it becomes necessary to do your job well for you to learn more about your particular job, your particular application, your particular field. And it also is very different in terms of the degree of collaboration that you are involved with when you're working in a job. And internships in STEM are generally very, very collaborative. The dreaded class project that, is, a team project, and one person is really carrying everybody on their back. That doesn't fly in in the real world. You have to properly collaborate. So getting that experience in an internship is enormously valuable.
Yeah, because they teach you, right?
Yes.
They teach you those I call it the scientific soft skills.
Yes.
Yes, that we all need. Just for the folks, so you just want to make the audience aware that the Department of Energy does have internships for college students through the Department of Energy, the Science Undergraduate Laboratory Internship. And if you are a high school student, Brookhaven Lab does offer an opportunity called the High School Research Program, which applications are open right now to do just that, to start that exploration process and to find out how is it, and that's that soft skills STEM education, as I call it, to get you into that career path that you may want to follow. One thing that you and I were talking for some time today, maybe before that, was the the value of a diverse and inclusive community, right? And in STEM fields in general, the number of Latinos and African American are reduced, and in computational sciences, the number of Latinos and African American women is even less than the overall STEM fields, right? Compared to other STEM fields.
Yes.
What would you say? In terms, what would you say, or what would you talk to? What are ways that we can, improve our representation in those areas?
Well, first, you're absolutely right that the STEM fields do have a representation problem, and computer science in particular has an even more so of a representation problem than the other STEM field does. And it's enormously important, not just from a representation point of view, because I view representation from the point of view of the student, the employee, like how you see yourself represented in this field, in this company, in this organization. But there's more to it than that. I think it's important because of perspective, because in STEM, science is about answering questions, and engineering is about solving problems. But the problems that you want to solve and the questions that you want to answer in a particular field, in a particular institution or organization, are going to be very different. They're going to look very, very different if everybody in that organization or in that field has the same background versus an organization or a field where there's a diverse background. And that perspective becomes very, very important because it changes what problems you actually even look at. So to everybody in the audience, if you see an important part of your identity not represented in a field or in an organization that is important to you in the STEM fields, then be that representation yourself, not just for yourself, but because you being there improves the field and makes the field stronger. The perspective that you can bring will make that field stronger. And that's ultimately one of the strengths of representation in STEM.
Well said. Thank you. You couldn't have said it any better. Actually, I'm glad that we're recording this, so I can always refer to that as a great answer. And I agree. Thank you. Thank you, Carlos. So before, if you have any questions, you're welcome to put it on the chat, on the Q&A section. Before we kind of wrap things up, I just want to go back because you mentioned coding classes, right? As the course I take. What other courses students, should be able to think about, or whether it's in high school or in college, pursue a field like yours? I'm thinking perhaps the mathematics as part of that as well.
Yes. Well, machine learning is not black magic, even though it sometimes looks like it. It's math. So if you are particularly interested in machine learning, the fields that you should look at and should acquaint yourself with are first programming. You need to be a good programmer to get anywhere with this field. But then you also need math, especially linear algebra and statistics.
Okay.
So if you're interested in machine learning or think you might be, take a look at those fields. If it's not offered by your school, look for online resources. There's lots of online resources for these fields. And the great thing about these online classes is you can pause and rewind and watch it as many times as it takes for it to sink in. I do this all the time. Most of my learning today is on YouTube. It is the best resource for learning so many things.
Yeah.
And so, yes, learn linear algebra, learn programming, learn statistics, and you'll have a great heads up on a career path towards machine learning.
And so there's a question on the chat asking, what programming language do you recommend students to learn?
I recommend Python. Python is first of all, it's a very easy language to learn compared to a lot of other languages. It's very comfortable. It's very intuitive. I like other languages, but some of them are a little hairy.
Which one is your least favorite one? Just wondering.
My least favorites. I do not care for Lisp. Okay. I don't like a lot of the old business style languages like Fortran and COBOL. And I unless I'm doing some embedded programming, I don't use C++ very much anymore. Okay.
Python. We're talking Python.
I recommend Python. Python is great, not only because it's relatively accessible and easy to learn, but because the skills that you learn in Python are obviously transferable to other languages as well. And because 90% of machine learning research is done in Python.
That is, yeah. And I hear that there are wonderful YouTube videos on how to learn how to code in Python and at least learn that structure.
Yes.
Okay. There is let's see, any other questions? I can see some stuff coming up. It's a question that says, hi, Carlos, what is your experience with Java?
Java. So Java is great if you are writing like apps. So if you're writing like apps for Android, you need to learn Java. If you're not writing apps for Android, I would skip it.
Okay. But Carlos, that's the the interesting part that you mentioned. A lot of the AP computer classes that most of the AP computer classes I believe are taught actually Java. So maybe start rethinking of.
Yes, there is staying power with a lot of these languages. So Java, obviously, C++, C# are the big languages because they are very, very flexible. They can do everything from very, very low level programming all the way up to highly abstract programming. I personally prefer scripting languages like Python because they're just so intuitive. They're so accessible and easy to use in very many contexts. You can write Java programs in a web browser and they'll do a lot of the things that you need them to do.
I love
that. And you get immediate feedback, and the library support for a lot of these languages is great. If you're already familiar with another language, learn more about it, definitely. I mean, leverage what you learned already, especially if you're learning it in class. But just know that there's other languages out there.
Yeah, you can build from there. Right? You build up from the skills that you know. There's a question in the chat that said, can you use machine learning to create more resilient machines such as those used in Fukushima in extreme environments where electronics and systems may fail? Thinking of space travel too.
Well, that's more of a hardware problem. Because the resiliency in situations where you have like radiation really concerns the effect that it has on hardware, like random bit flips, for example. But you can make the software that runs on that hardware more resilient to those kinds of errors, including with techniques like machine learning. But it's not the only way to do that. There are other ways.
So isn't the software can kind of learn, predict what those flips would be, for example, if they were going to space.
You can make your programs resilient to these kinds of failures. It doesn't need to be done with machine learning, but it's one approach. Well,
I think we're pushing towards 4:45. This has been very cool, actually. And I'm glad that you are with us today, because I've been wanting to do something with computer science, and you and I met last summer, and I said, Carlos is the person to do this. So thank you,
Very glad
Carlos.
to have been here.
So before we go, if the audience forgot anything that you just said today, what kind of 2 words of advice that you want to leave them with?
Okay, the 2 things that you should walk away with: self-learning. Don't just restrict yourself to what you learn in class. Go out of your way to learn on your own. There are so many resources. There's no excuse not to. And the other is hands-on experience. Build something yourself, not just the little, not just what you need to learn to learn the topic, but build something out of that you think is useful. Make a game of Tetris, buy a $5 Raspberry Pi and make a automatic cat feeder. There's so many little projects that you can build, and in the task of building those projects, you learn so much more than you would any other way.
That's awesome advice. I like the Arduino for the cat feeder. I will ask my daughter to do that. So thank you, Carlos, for being our guest today. It was a pleasure. Our next Science Thursday will be March 17th. So it will be Ashley from the Center for Functional Nanomaterials. I'd like to thank Brookhaven National Laboratory for hosting this event today, and encourage you to check our programs for research and internship opportunities at the Office of Educational Programs of Brookhaven National Laboratory. We will post this on our Science Thursday. Video will be posted in about a week or so, so keep an eye out for it. Thank you, Carlos. Thank you so much. Thank you to an audience. Have a wonderful, wonderful day.